All right, so this is the review session for EGME 541, spring 2022 semester for the second midterm. Okay, so I looked at the poll online and we have two winners. And so the two winners for our review session are going to be number one, approximate solutions to weak forms, and number two, heat conduction in 2D. Okay, all right, so let's go ahead and get started. And we'll start with approximate solutions to weak forms. Okay. All right, so we have here our approximate weak form solutions. And so I think the best place to start would just be to describe, what the weak form is, right? And so the weak form is, nothing different than just our regular boundary value problem. It's just expressed in a slightly different way, okay? So remember, that's always the first thing to remember, that, when we're talking about weak forms and strong forms, the two are exactly the same thing. It's just that we're expressing the problem just in just different formats, okay? Okay. All right, and so the most general form of the weak form is the following. And so we have, the integral from 0 to L, L being the length of our domain of dw dx times k times a times dt dx is equal to integral from 0 to L w of x s of x dx plus w dot ka dt dx. Okay, and of course this is for heat conduction. All right, so that's our weak form. And so remember, the way that we obtained this weak form was that we took our strong form equation, which in this case was our heat conduction equation. We multiply it by our weighting function. We integrated it over the domain, and then we perform integration by parts to balance the derivative term, okay? All right. And so this is the weak form. And so, it's I know, I say it constantly that, the weak form and the strong form are the same problems. And so when you solve it, you get the same thing. It's just that the way we usually solve these in practice, in terms of the class, we just always end up solving approximate solutions to weak forms. And so, these solutions that we obtain through this method they're different than the strong form solutions, but it's not because the weak form itself is different. It's just that the way that we approach it. Okay, and so the key word here in this section is approximate solutions. Okay, you could very easily find approximate solutions to the strong form as well, using a very simple method. It's just that the reason we do this for the weak form is just because it's kind of a precursor to finite elements, because that's kind of how we do it with finite elements. Okay. Okay, and so with that said, let's kind of break this down a little bit, and talk about the different features of this functional form, right? And so first, let's talk about W. So that's kind of the big thing about weak forms. Okay, and so W of x, of course, is our weighting function. And it's something new that we added to the weak form that obviously is not there in the strong form of the equation. Okay. And what is it? And so, the weighting function kind of serves, a few different purposes. But the main purpose that we have for it is that it's kind of meant to draw out one of the derivatives on our solution variable. Okay. In particular, I'm talking about this this integral right here. Okay. All right, because normally, if you look back to the strong form of this equation, and elasticity has the same thing. We had, I'll just draw it here for a second. We had a second order derivative with respect to the temperature, right? So a d squared t dx squared. That is fine. It's fine to have a second derivative. There's nothing wrong with that. But it puts a little bit more restrictions on the solutions that we can assume for it, right? And so in particular, what this allows us to do is that if we have a second order derivative, let's try plugging in a linear function into there. Okay? And so if you plug in a linear function into a second order derivative, you end up with nothing. You end up with 0, right? Because you take the first derivative, the constant term goes away, the linear term, becomes a constant. You take the derivative again, and then the whole thing just goes away. Okay. And so with a second order derivative, you're kind of forced to use a quadratic function, if you want to plug in an approximate solution, right? And so the benefits to using this weighting function is that now in this form of the equations, we only have first order derivatives, right? And so we have first order derivatives here, and then no derivatives anywhere else, right? So this is a big bonus for us because now what we can do is if we plug in a linear function for both w and t, it's not just going to go away. We still have something that we can work with, right? And linear approximation functions kind of form the backbone of a lot of finite elements. If anything, just the initial phase of finite elements when you're first learning it on the go. Okay. Okay, linear finite elements and linear shape functions. Okay. Another requirement for the weighting function here is that it has to disappear at the locations of our Dirichlet boundaries, at the locations for our essential boundaries. Okay. And by disappear, all I mean is that it has to equal to 0. Okay. Right. Because what you'll notice from the weak form is that one nice feature is that if you look at this term right here, and I'll circle it in green. Okay. Right. Another nice unique feature about the weak form is that the Neumann boundary conditions are baked right into the equation, and so we don't have to do anything extra to satisfy it. Okay. Okay. And so that's really nice. And so, as we're going about solving the weak forms, we don't have to do anything special for that, right? If you recall, when we did our strong form solutions, when we were applying our boundary conditions, right? Or, when we were going through just the general solution procedure, right? We would get a general solution for the strong form, right? In terms of C1, C2, and then we have to apply both our boundary conditions individually in order to obtain our, our specific solution. For the weak form, we don't have to worry about that or at least not for one part. And so, the Neumann boundary condition is baked right in. And so that's already going to be part of our governing equation. So we kind of solve it all at once. Okay? What's not baked into here, though, is our Dirichlet boundary conditions, or the locations where we specify the solution variable directly. Okay. And so just like the strong form, we can have to do that separate after we're kind of done with I guess in weak form case, we do it kind of before, right? And so, when we have Dirichlet boundary conditions, in order for the solution to work out, the weighting function has to disappear at those locations. Okay, and you'll see how we apply that, once we kind of work through an example. Okay. Okay, let's see what else. And so another thing about the weighting function is that in order for us to get a good solution for this, it has to have the same functional form as our solution. Okay. Okay. And you'll see very soon, and so that'll be the next point that we cover, that that in order to solve for approximate solutions, the first thing that we have to do is we have to assume, a functional form for the solution, right? So we have to either assume that it's a linear function or a quadratic one, right? And so in order for this to work, then the weighting function has to take that exact same functional form. Okay, so kind of keep that in mind as we're working through our simulation, or working through our solution. Right? Okay, and so back to that point, right? And so, so that's kind of the properties of the weak form itself. Now let's talk more about what it means to have an approximate solution. Okay. Okay, so this part's probably a bit different than probably what you're used to in terms of solving for solutions. It's usually when you're presented with a problem, you follow some kind of recipe, you follow some kind of problem solving methodology, right? So we saw that with the strong form, and then you usually arrive at a solution, and then the solution just takes whatever form it takes, based on the procedure that you followed and the nature of the equations. Okay. To find an approximate solution, you kind of take that process and you kind of invert it on its head. And so you start with the solution itself. Okay. And so what you say for approximate solution is that I'm going to make an assumption. I'm going to make an assumption of what the solution is going to look like, and then I'm going to solve. And then, based on this assumption, I'm going to solve for the solution. I'm going to solve for the best form of this assumed solution that best fits this problem. Okay. And so the first step in getting it an approximate solution is that you have to assume its functional form. Okay. And so 99% of the time, at least for practically speaking, these functional forms these functions take the form of some polynomial. Okay. And practically speaking, the only ones you can actually do on an exam are just linear and quadratic functions. So that's the only two types that you can feasibly do. Okay. Okay. And so as an example, let's say that we are assuming a quadratic function. Okay. And so what you say at the very beginning is that I'm going to make the decision right now that my solution is going to be some quadratic function. Okay, and so we're going to have t of x is equal to a0 plus a1x plus a2x squared. Okay. And so that's the most generic quadratic function that we can think of, right? And so it has the x squared term, which makes it quadratic, and then it has all the terms before that as well. So a0, which is our constant term, a1x, which is our linear term. Okay. Right. And then going back to this point we made above with the weighting function, if we're assuming that our solution is a quadratic function, that means our weighting function as well has to be a quadratic function as well. And so we have w of x is equal to b0 plus b1x plus b2x squared. Okay, and so they have to be the same. And so if they're not the same, then the method doesn't really work out. Okay. Okay, and so I think that's all the basics in terms of strong and weak forms that I want to go over. Let me just kind of scroll through just to make sure. Okay. Yeah. Okay, and so I guess the last thing to note is that, you know, remember that these are just approximate solutions. And so, you know, sometimes these approximate solutions will match the exact solution, but that's not always the case. Okay. Okay. And in fact, you know, there's a specific case when they do match, right? And so your approximate solution and exact solution will match. You know, in mathematical terms, we say that when they span the same functional space. Okay? So that's kind of a fancy way of saying that, you know, if our exact solution has the same functional form as our approximate solution or contains the same terms, then our two solutions are going to match. Okay. And so for this case here, you know, where we have this quadratic function, you know, that's going to match up with our exact solution if our exact solution is a quadratic function or less, right? And so if our exact solution is quadratic, then, you know, our approximate solution is going to match together with that. If our exact solution is linear, okay, since we have the linear term here, and that's going to match exactly. Or, you know, and it's rare, but it can happen. If the exact solution is just simply a constant, then our approximate solution will pick that up as well. Okay. But, you know, if our exact solution has a term that's outside of this functional space, and so let's say our exact solution is like x cubed or x to the fourth, then our approximate solution is not going to match that. But what it's going to do is that it's going to find the best quadratic function to match up with that, you know, with that exactly. Okay. Okay. And so to that end, let's go ahead and do an example, because I think that's what people are probably mostly interested in. Okay. And so let's do problem 3C on the homework. Okay. Okay, so this is problem 3C on homework 3. Okay, and so in this problem, you know, you're asked to compute the approximate solution to problem 2B, but with you know, with the quadratic function. Okay, so actually I should have pulled this up. So let me go ahead and pull up the problem. Okay, 2B. Okay, so 2B. This is our hanging bar structure. Okay, and so we have a structure that looks like this. Okay, we have a bar that's hanging down. Okay, we're going to say y is equal to 0 is the top of the bar. Okay, the bar has a length L, where L is what? Is 6 meters. Okay. The Young's modulus of the bar. Sorry, I have a sneeze coming up. The Young's modulus of the bar is 500 Pascal. Okay. And the cross-sectional area of the bar is going to be a constant. Cross-sectional area is 0.8 meters. Okay, so that's great. So actually, our your E and A is constant. Okay. All right. You also have a vertical load here, and so the vertical load P has a magnitude of 100 newtons. Okay. And we have a body force. So the body force is going to be, you know, present throughout the entire rod. Okay, this body force is meant to represent the weight of the bar. And so the body force is given by function 30 plus tan y. Okay. And so from this problem, we're going to be asked to compute the approximate solution, assuming a quadratic form. Okay. Okay, and so we're going to assume that u of y is equal to a0 plus a1y plus a2y squared. That means w of y also going to be a quadratic function. b0 plus b1y plus b2y squared. Okay, all right. And so let's go ahead and begin. Okay. All right, and so the first step that we need to do, before we get rolling, is to apply our Dirichlet boundary condition. Okay, and so for a structural problem like this, a Dirichlet boundary condition takes the form of a fixed support. Okay. Okay, fixed support boundary condition. All right. And so that kind of makes things easy. And so that that means we're going to have basically the same values for the constants in u, y, and w, y. Okay. All right. So if we look at the problem geometry for this one, we have our fixed support at y is equal to 0. Okay. And so our fixed support is going to be u of 0 is equal to 0, right? Because that's the Dirichlet boundary condition. And so we plug in y is equal to 0 here, and we get a0 plus a1 times 0 plus a2 0 squared. Okay. All right. We go ahead and evaluate this. Everything multiplied by 0 is just going to be 0, and all we're left with is a0 is equal to 0. Right. And so normally when you apply a Dirichlet boundary condition, you should be able to solve for one of the constants in your approximate solution. Okay, and so in this case, we get the value for a0 just straight up. Okay? And it makes things easy because it makes it equal to 0. Okay? All right, so now let's apply that condition to the weighting function. And remember, our requirement for the weighting function is that our weighting function has to disappear at the Dirichlet boundary condition. Okay. All right. And so if w is going to disappear, then it's going to be equal to 0. And that's going to be when y is equal to 0, right? So we have w of 0 is equal to 0. So this is equal to b0 plus b1 times 0 plus b2 0 squared, right? We go ahead and evaluate that, and we get b0 is equal to 0. Okay. Okay. All right, and so now that we solve for a0 and b0, we now have, we're now left with two constants. Okay. Okay. And so now the next step is to basically just plug this into our weak form and solve for the remaining two constants. And when I say remaining two constants, I mean the ones in our solution vector. And so, we don't really care what's going to happen to our weighting function. It's just there to kind of help us out for a second. Okay. Okay. And so let's go ahead and do that. And so if we want to plug it in, we have to take the derivatives of our functions as well, right? So let's go ahead and do that. And so we take du dy. So du dy here is a1 plus 2 a2y, right? And we take dw dy, that's equal to b1 plus 2 b2y, okay? And so let's go ahead and plug this into our weak form. And so we plug into the weak form, we have integral from 0 to L of dw dy, okay? I know our original weak form had derivatives with respect to x, but x and y, as long as it's still 1D, you can kind of interchange one or the other. Okay, so dw dy, e times a du dy is equal to integral from 0 to L of w of y, b of y, dy, plus our Neumann condition term. And so our Neumann condition term is w dot ea du dy. Okay, we're evaluating this at the Neumann boundary. And so if you go back up to our problem geometry, our Neumann boundary is going to be at the bottom, right? And so that's going to be at x is equal to, or excuse me, y is equal to L. Okay. Okay. And so we have everything here. So let's just go ahead and plug in. And so we plug in for everything. We have integral from 0 to L. We have dw dy. dw dy is b1 plus 2b2y. Okay. Okay. We can plug in for E and A. And so E is what, 500, and A is 0.8. And so that's going to give us 400 here. Okay. Right. So this was a result of E times A. Right. Luckily, they're both constants, and so that's good. And then we have A1, du dy, which is A1, plus 2A2y. Okay. And that's dy. Right. This is equal to w of x, w of y times b of y. Integral of that. So we have integral 0 to L. Wy is b1y plus b2y squared. Okay. Then b of y here is 30 plus 10y, right? Y, because that was our b function here. Okay. And finally, we have the Neumann boundary condition. And so the Neumann boundary condition, you know, these two combined, these two are equal to t bar. Okay. And so if we multiply a by t bar, that's actually going to give us p. Okay. And so we plug into all of that, that's going to be w of L times, should be a negative p, I believe. Right. Or positive p, excuse me. Okay. Yeah. Okay. Right, let me just double check that real quick. Yeah, okay. And so p here has a value of 100, and so that's where it goes right there. Okay. Okay, and so, you know, just again, the way I obtained that was, you know, I know that if you take E times du dy, right, this is essentially stress times strain, and so that's going to equal to the stress, okay, or Young's modulus times strain, and so that's going to equal to stress, okay. And so if we multiply this the stress by A, what you get is a force, and we know that the force load that's being applied at the end of the bar is P, okay, and so that's why I get W of L is equal to P. Okay. Okay. All right. And so with the knowledge in mind that L is equal to 6, you know, let's go ahead and let's go ahead and evaluate this. Okay. And so we have next step 400. We're going to take this EA. I'm just going to factor it out. Integral from 0 to 6. Okay. And I'm going to distribute this, but I'm going to distribute it in a way that keeps the B1 and B2 terms separate. Okay. And that's going to be important because the B1 terms are going to act as one of our equations for our, you know, for our linear system, and the B2 terms are going to act as the other ones. Okay. Okay. And so here, let me go ahead and write it down. Distribute, but keep B1 and B2 separate. Okay. All right. And so we have B1. Okay. B1 times A1 plus A2y plus B2, and it's gonna be the same thing, just multiplied by y. So we have 2, or excuse me, 2 A2y multiplied by 2y, excuse me, plus 4. Sorry, messing all up. Sneezes got me all messed up. All right, so it's 2 A1y plus 4 A2y squared. Okay, dy. Okay, so I distributed it through, but then I kept the B1 and B2 separate. Okay. All right, this equals 2, and so I'm going to do the same thing with the body force term integral. And so I'm going to distribute these two terms together, but I'm going to keep B1 and B2 separate, just because it's going to save us some work in the end. Okay, and so this is equal to integral from 0 to 6 of B1 times 30y plus 10y squared plus B2 30y squared plus 10y cubed dy. Okay, so same thing there. And finally, we have P multiplied by W of L. Okay? And so remember, L is 6. And so if you evaluate that, then that's going to be equal to 100 times. Okay, we evaluate W at L, and so what we get is 6 B1 plus 36 B2. Okay. All right. Okay, and so now we're going to go ahead and perform the integrals. Okay, and so we perform the integrals, and what we get is 400 times. Okay, and so we're going to integrate this first integral up here, and so we're going to end up with B1 times. Okay, so since the lower integration down here is 0, I'm just going to ignore it because everything's multiplied by L and or by by y anyway. Okay, and so we have A1 times L, so that's going to be 6 A1 plus A2 L squared, and so it's going to be 36 A2. Okay, plus B2 times A1 L squared, so that's going to be 36 A1 plus 4 over 3 L cubed. So I don't actually have it right now. So it's 4 over 3 times 6 times 6 times 6. And so that's going to be 288 plus 288 A2. Okay. And so that's the first integral. And so that's the derivative term. Next we have the source function term. Okay. And so there's B1 multiplied by we have 15 L squared, and so we have 15 L squared plus 10 over 3 L cubed. Okay, and so you plug all that in, and what you get is 288, or excuse me, 1260. Okay, plus B2 times 10 L cubed plus 5 over 2 L squared. Okay, you plug in the numbers for this, and you get 5,400. All right. So that's the body force term. And then from here, you're going to add the remaining terms for the Neumann boundary condition. So we have a plus 600 B1 plus 3,600 B2. Okay. All right, and so this is good. And so, we're getting very warm, right? And so the next step that we're going to do is that now that we have everything in terms of numbers here, we can form a set of 2 equations and 2 unknowns. Okay. Okay, and the way we're going to do that is we're going to say that all our B1 terms all our B1 terms will become one equation. Okay. And then all our B2 terms will become the other equation. Okay. And so we're going to have two equations, and we're going to use those equations to solve for our two unknowns. Our two unknowns here being A1 and A2. Okay. All right, so let's go ahead and let me first combine all the B1, B2 terms, and then we can go ahead and form the equation from there. Okay. All right, so first we have B1. And so we're going to go ahead and collect all the terms on the left. And so if we go ahead and distribute this 400 through, right, then what we're going to get is B1 times 2400 A1 plus 14 400 A2 is equal to, we have 1260 minus 600, right? So that's our first equation. Then we have B2. We combine all the B2 terms together. And so what we end up with is 14 400 A1 plus 11 5200 A2. Okay. And this is equal to minus 5400 or excuse me, equal to positive 5400. Plus, hang on, minus 3600, excuse me. I think I forgot to, the fact that P is negative, I forgot that fact here, right? And so, you know, if we go ahead and correct this, that means that this is going to be negative and this is going to be negative, right? So that's how we kind of correct for that, okay? Okay, yeah, so I did that problem, you know, assuming that P was positive, but P should have actually been negative, okay? Okay, so let's go ahead and solve these two equations, right? And so this is going to be, you know, a two equation, two unknown system. And so, you know, you can solve this in MATLAB, okay? You know, of course, for an exam, you know, you don't expect to get a system of equations like this. And if you do, you know, it's going to be easy to solve, okay? And so with that in mind, you know, if we go ahead and solve for the constants, then what we get is A1 here is equal to 1.225, and A2 is equal to minus 0.075, okay? And so we plug that in back to our original equation, and we get U of y is equal to 1.225 y minus 0.075 y squared, right? Because these A1, A2, you know, they eventually go back and plug in to our original assumed form, which was up here, okay? Okay, and so I think that's a good example to do, because we kind of, you know, saw everything in this problem. So we saw Dirichlet boundary conditions, we saw Neumann boundary conditions, you know, we plugged into the weak form, you know, we found our solution with a quadratic approximate function, okay? And so for the exam, you know, this is probably a little bit too much work to do on the exam, because, you know, on the exam you have a little bit less time, you know, but you know, this process is always good to be familiar with as you study. Okay. Okay, so I think that's about all I have to say about weak forms. So let's go ahead and move on. And so the next thing I want to review, based on the poll, is 2D heat conduction. Okay. Okay. All right, and so in terms of calculations, I can't really expect you to do any calculations with regards to 2D problems. And so what I'm going to do instead is I'm going to go to the study guide, and let's go ahead and answer all of the learning objective questions that have to do with 2D conduction. Okay. Okay. So number one. And so, going through the study guide, is always a good idea when you're studying, just because it's, the exam's going to be based on that study guide, right? Excuse me. All right, so number one on the study guide is to characterize the problem domain and boundaries for 2D heat conduction problems. Okay. All right. And so this just has to do with kind of general 2D finite elements, right? And so, when I say to characterize the domain, I really mean to kind of differentiate this between the 1D case, right? And so in the 1D case, we have a line, which is our computational domain, right? But in 2D, of course, our domain is going to be, much bigger, right? Or I guess not necessarily bigger, but more dimensions, right? And so if you were to characterize, the typical domain for a 2D finite element problem, I would call it a surface, okay? Right? A surface is the name that we typically use for, a two-dimensional object, right? And so for all intents and purposes, we're going to assume that our surface is flat on the table, okay? Okay. And so our domain here is a 2D, a 2D space. It's going to be a surface like that, right? And then our boundary around our domain here is, of course, going to be a line. Right? Okay. Right. And so that's the domain. Right? So typically speaking, when you're talking about domains and boundaries, the domain, the domain is always going to be the same kind of dimensions as your space, right? And so for solving 2D finite elements, then our domain is going to be a 2D geometry, a 2D entity. Okay. And then if you talk about the boundary is going to be one dimension, always going to be one dimension less than the domain. Okay. And so if our domain is 2D, then our boundary is going to be 1D, right? And if we saw in 1D, if our domain is 1D, right, if it's just a line, then our boundary is just one step down from a line. And so what's one step down from a line, you ask? It's points, right? And so we talked about the endpoints. And we can extend the same logic to 3D as well. And so for a 3D, our 3D domain is characterized as a volume, right? And then the boundary around that volume is surfaces, right? So 3D domain, 2D boundary, 2D domain, 1D boundary. Okay. And so if you draw a picture like this and kind of explain it like that, that's a good way to go. Okay. Right. Number two. Number two is to state the strong and weak forms of the 2D heat conduction problem. Okay. And so I just want you to state this, and so you don't have to derive it at all. Okay. But I just want you to kind of know what they look like. In particular, I want you to know what the weak form looks like in terms of all the vector calculus operators that we had before. Okay. Okay, so let's do strong form first. And so strong form, what we have is K. Right, we have K times partial squared t, partial x squared, plus partial squared t, partial y squared, okay, plus s of x and y is equal to 0, okay? Okay, and so if we convert this to vector algebra form, then that first term there becomes the Approximate. So we have k times partial squared t plus s of x and y is equal to 0. Okay. So this here is our strong form. Okay. Then, of course, just the general progression is that we take our strong form here, we multiply by our weighting function, and we get the weak form, right? And the weak form for 2D heat conduction has the following form. And so we have double integral of the gradient of W, okay, times K, gradient of T, dA, right, is equal to minus line integral around the boundary of W Q vector. So that's our Neumann boundary condition term, plus double integral of W times S dA. Okay. All right, so this right here is our weak form. Okay, and so of course, the weak form was a result of us performing integration by parts. Oh, fuck, I missed. On our strong form, right? And so, when I say I want you to state this, I also want you to be able to characterize what each of the terms in this expression mean, okay? And so, of course, we have this right here, right? And so you can see we have two gradient operators here. So we have gradient of W and gradient of T. And so what this here represents is our balanced derivative term. Okay. Right. This term, is the only term here that's not a double integral, and so that's because it's a line integral around the boundary. This is our Neumann boundary condition term. Okay. And then this term right here, this is our thermal generation term, or in other words, our source term. Okay. And so that last term provides, it provides contributions to the element forcing vector from some kind of body force or some kind of thermal generation, something that's persistent throughout the entire domain. Okay. Okay. Right, and so that's kind of the the weak form for that. And so I want you to be able to write these down. I want you to be able to identify each of the terms and explain kind of what they mean. Okay? And then finally, our last learning objective here is to state what the element interpolation function for a rectangular element and explain how this complicates things for the computation of element stiffness matrices. Okay, so it's kind of a long one, but it's kind of explains kind of the big difference you see in rectangular elements versus triangular elements. Okay. Okay. All right. And so to explain this, we have to kind of look at what first look at how the triangle looks like. Okay. And so here's our 3-node linear triangle. And I guess I should say, let me append this. This should be for linear triangles in particular. Okay. And so for our linear triangle, we have 3 nodes. And so with 3 nodes, that means our element interpolation function can have three terms in it. Okay? All right, and so if we have all linear terms and we have 3, this makes it pretty easy for us. So we have A0, right? So we have our constant term. We have our term that's linear in x, right? So we have A1x. And we also need a term that's linear in y as well. So we have A2y squared. Okay. And so with triangles, things actually work out really well because you have, just perfectly linear terms or constant terms for all the terms. Okay. For a rectangle, it's a little bit different. Okay. And so for a rectangle here, we have 4 nodes. And so with 4 nodes, that means our element interpolation function has to have 4 terms in it. Okay. Okay, so if we have t of x and y is equal to A0 plus A1x plus A2y. And so all of those are going to be the same as the triangle, but we have to add one more term, right? Because with 4 nodes and 3 terms, we end up with an overdetermined system. And so to rectify this, we have to add one more term, but we're all out of linear terms. And so we don't have any more linear terms that we can actually add to this and still make it a good system, right? And so we have to kind of make this extra term here, which is I like to call it pseudo-linear. Okay? So it's going to be an A3x y. Okay? This term right here is actually going to cause us some issues. Okay? In particular, in the element stiffness matrix. Okay? Because if you look at our balanced derivative term, right, and so we know that's the term that eventually becomes our element stiffness matrix, we only have first order derivatives here, right? And so we take the gradient of something, you end up with first order derivatives. Okay. When you do that for the linear triangle, that's really nice because when you take a first order derivative of every term here, no matter what, you're going to end up with a constant, right? You take the derivative with respect to x, you get A1. You take the derivative with respect to y, you get A2. Okay. And so that's really nice because when you take those derivatives, you end up with a constant, and that integral becomes, usually pretty easy to evaluate. I mean, it's easy in terms of arithmetic. It's also very annoying in terms of arithmetic just because there's a lot to do, but at least you don't have to integrate, and that's always a plus. Right? That's not the case here with the rectangle. So for the rectangle, if you take the derivative of t with respect to x, right, you just take the first derivative, it's true you're going to end up with the same constant term here, A1, but that last term is not going to go away. It's not going to go away, and it's not going to be a constant either. It's still going to have a function of y, right? And same thing happens when you take the derivative with respect to y as well. And so what ends up happening is that your expression for your element stiffness matrix has a lot of extra x's and y's kind of floating around a bit. Okay, if you combine that with all of the matrix multiplication you have to do, you end up with a 4x4 matrix. Then performing that integration actually becomes a really big pain actually. And so it's to the point where it's just not practical to do it by hand. So of course you can write a computer software to computer program to do that for you. But even that's annoying, just kind of based on just how many terms it is, and even if you do it with Gauss quadrature, okay? Which we will do eventually. That's kind of what we're working on right now. But it's usually not a fun thing to do. Okay. Okay, and so I think that about wraps it up. And so there's a lot in our lecture notes for 2D heat conduction. But a lot of that eventually is going to be worked into your project. And so for this exam, the exams are always tricky because you have a limited amount of time, and so there's always going to be a limit, or there's always going to be a constraint of how much I can ask you to do. And so the problem with 2D is that everything there is so computationally expensive, it just takes so long that that places a big limit of what I can ask you to do. And so for 2D, I do want you to understand that some of the conceptual stuff, especially with regard to these 3 learning objectives that we just went over, But beyond that, you know, I can't really ask you to do it anymore. So, you know, that's what you should focus on for this exam. Okay, all right. And so I'm going to go ahead and close it up here. So best of luck studying. If you have any questions about anything, you know, please don't hesitate to let me know, and I'd be happy to answer for you. Okay. All right. Thanks.